we're going to bring everything that we've done together so far into this, what's called the quantum number of an electron. And what the quantum number tells us is basically the address of an electron, right? We said at the beginning of the chapter that was going to be kind of our overall goal. And so we worked through the configuration of electrons to get there. We worked through the diagrams. Do you remember what those are called? No.
Orbital notation.
Right, orbital notation. When we draw our electrons, we worked through all of that to get to this point. And so this is called the quantum model. This is what we've been working towards, is being able to show our electrons in these different orbitals, the different orbital pockets. Basically, a quantum model ends up looking as like an electron cloud, right? Because there's more shells closer to the nucleus. The s and the p orbitals tend to hold the most electrons because there's more of those orbitals, and they're closer to the nucleus. So this little cloud you kind of see here is considered the quantum model. It's just the denser region is toward the nucleus of the electrons, and it gets less as we move out. Excuse me. So we're going to talk about the quantum number. Before we can get into that, I want to think about the irregular address. So here's the address to the school. There are 4 parts. Oops. 66002. There's 4 parts to the address. I just erased it. All right, 4 parts to the address. The number, the street, the town, and the zip code, right? 4 parts to the address, 4 parts to any address. The same is true for a quantum number. There's 4 parts to any quantum number. But the way a quantum number is written is like this. 4011/2. Right? That's an example of a quantum number. It's written with parentheses. It's got 4 values that are separated by commas. Okay? That's the format for a quantum number, or for an address of an electron. Okay? The format is like that. So when I ask, what's the quantum number of something, you're not going to tell me 6, because that doesn't mean anything. The quantum number has 4 parts. Okay? So I'm going to talk about what each of these 4 parts mean, and then how we can identify them. All right, I'm going to give you just a brief list of what they mean, but I'll dive deeper into them so you don't have to write them down right now. The first part of it is called, or gives us the main energy level of the electron, or the shell. The second tells us the shape of the orbital that electron is in. So is it in an S, a P, a D, or an F orbital? The third one tells us the orientation of the orbital, or what version of the orbital it's in. And then the last part of the quantum number tells us, is it the positively spinning electron, or is it the negatively spinning electron? Okay, it tells us the spin state. So I'm going to talk about each of these 4 parts more in depth. So don't feel like you have to get them written down right now. We're going to talk about each of them a little bit more. Okay? All right, so the first part is symbolized by an N. Okay, I'm going to write this up on the board so that we can see it. But quantum numbers are N, L, M, and then MS. That's what they're abbreviated by. I wouldn't worry too much about knowing the letter necessarily that goes with it, but the N value is the one that always comes first. So N, then L, then M, then MS, right? This is what comes first. And it tells us the principal energy level, or the main energy level of the electron, or what shell it's in. You can think of it that way too, what shell it's in. Okay, so let's say I was looking at, sorry, am I going a little bit too fast? Let me give you a second. Let's say I was looking at the last electron that goes in chlorine. The end of its electron configuration would be 3p5. Agreed? For chlorine? Okay. So the main energy level would be 3. That's it. That's all you have to do. So the first part of the quantum number, if we were looking for chlorine, would be 3. Okay? Because the electron that we're trying to locate, the last electron for chlorine, would be a 3p5. So if I was going to draw it in orbital notation, 1, 2, 3, 4, 5. This is the electron I'm looking at right here. Oh.
Yeah.
Sorry, I didn't know it was lagging. But the first part of the quantum number, all it tells us is what energy level or what shell it's in. That's it. So the first part of the quantum number comes right from that 3, comes right from this 3 in front of the shape. That's it. Okay? So if my quantum number, or I'm sorry, if I had another example, let's say I had 4D, 1, 2, 3. Okay, what would the first part of my quantum number be in this example? 4. That's it. Right? Because it comes right from here. Okay, so the first one's really, really easy. Really, the first 2 are really easy. So the first part of the quantum number just comes from what shell number it's in. The second part we said tells us the shape of the orbital. How many different orbital shapes do we have? S?
4.
Good, we have 4. S, P, D, and F. Okay, the second quantum number is given with an L symbol, and it tells us the shape of the orbital. So this is like as best as I could do for a cursive L. Okay, that's just what it's symbolized with. N, then L, and then M, then MS. So the second part tells us the shape of the orbital. There's only 4 options, S, P, D, or F. And so each of those shapes have been assigned a numerical value. And I'll have that table for you on the next slide. Okay. Here's the table that I think you need to have in your notes to give you the values of L. Okay, here's L. I don't know why my cursive L went away. But if it's an S orbital, it's going to have a 0. If it's a P orbital, a 1. A D orbital, 2. An F orbital is going to be given value 3. So this one, while I'm doing my quantum numbers, I often just literally say it out loud that S is 0, P, D, F. Right? S, P, D, F. That's it. Okay? So as I'm remembering my quantum numbers and I'm trying to figure out, okay, I know the energy level, I know the shape, S, P, D, F. And it'll tell me the value that goes with it. Okay? So the way we find quantum numbers is often using the orbital notation of the element. So let's go back to our example with 3P, sorry. With chlorine. 1, 2, 3. And we said we were looking at this electron. Right? So we already said that if we were going to write the quantum number for that electron, our first principal quantum number would be 3. What would the second one be? 1. Good, because it's in a p orbital. And so if it's in a p orbital, it's got to have a value of 1. Okay, that's it. If it's in a p orbital, it's got a value of 1. So the first 2 parts of our quantum number are really easy to find. Okay? What questions do we have about these first 2 parts? Okay, what if I had a 4s orbital? How would I start the quantum number? 4, then 0, right? And then I'd have something else. What if I had a 3d orbital? How would I start the quantum number? 3, then 2. Very good. What if I had a 1p orbital? Not possible. Right. Are there such things as 1p orbitals? No. And 1s would be 1, 0. Right? 1s would be 1, 0. Okay? So we feel good about picking out the first 2. Okay. Now we need to start looking a little bit more in depth at orbital notation and how it relates. But the third quantum number, right? First one tells us energy level. Second one tells us shape. Third one tells us what's called the orientation of the orbital. But more specifically, or how we need to think of it as, what version of the orbital is that electron in? Okay? What version of the what version of the orbital is the electron in?
So would that be where orbital notation comes
Yeah, we're going to be able to look at those lines within our orbitals and say, oh, it's on this one, and we're going to look at that. Yeah, that's a good question. Okay, values of M are whole numbers including 0 from negative L to positive L. Okay, and that seems pretty abstract right now, but when we see it drawn out, it's going to make more sense. I want to go back to the example we've been looking at. Okay, we've been looking at this electron right here. So far our quantum number was 3, then 1, and we still have 2 more parts we need to fill in. Okay, so we've got the N value, which is 3, energy level, the L value, which is 1, the shape. Next one tells us what version of the orbital it's in, right? There's 3 versions of the p orbitals. Here's 1 version, here's 2, here's 3, right? 3 different versions of the p orbitals. So we got to tell which version it's in. And we said that values of M are whole numbers that range from negative L to positive L. Here's our L value right here, 1. So they need to range from negative 1 to positive 1. Here's how we figure out which one it is. We write underneath them, negative 1 to positive 1. Negative 1, 0, positive 1. Those are our 3 different versions of our orbital. Right? Really, we know they sit on the x, y, and z axis, but this is how we tell which version of the orbital it's in. Okay? We say negative 1 to positive 1. Okay? If you can't remember that it's got to be the range of negative 1 to positive 1, just start in the middle with 0, then work outward from there. Okay? So what version of this orbital would it sit on? What would be the next part of my quantum number? 0, right? Because that's what orbital that electron is at. That's it. Okay? So you'll go to orbital notation, you'll label your individual orbitals, figure out which one is the electron I'm looking at, which one is it on, and that's my 3rd part of my quantum number. Yeah, Kevin. All right. Very last part is the spin state. It only has 2 possible values, either positive 1/2 or negative 1/2. That's it. 2 possibilities. It's got to be one of those 2. All it tells us is this electron the positively spinning electron or the negatively spinning electron? Let's look one more time at the one we've been working on. So here's 3p. 1, 2, 3, 4, 5. This is the electron we're focused on. We said so far the quantum number is 3, 1, 0. What do you think the spin state's going to be? Is it pointing upward or pointing downward? It's pointing downward. So my last part is just negative 1/2. Okay, if it was positive 1/2, we'd be talking about this electron here. Right? The first one that went in. But we have negative 1/2, right? So it's the second one that went in there. Okay, the positive one is this one right here. The negative one's the one we're examining. That's it. That's the 4 parts. Okay? Energy level, shape, version, spin. The 4 parts. Okay, what questions do we have? Let's try some. Okay? We almost always, when we're talking about quantum numbers, it'll say, find the last electron placed in whatever element it is. That just means we want to focus on the very last one. We're not looking at an earlier one because we could solve that differently. But all right, find the quantum number for the last electron placed in arsenic. So let's locate arsenic first. Tell me approximately like what block is it in? 1s, 2s, 2p, where is it at? 4p. 4p, I would agree. It's 4p. So the easiest way to do quantum numbers is to go ahead and draw out the last part of its orbital notation. Okay, so draw out the 4p orbitals. And arsenic is 4p, 1, 2, 3, agreed? Arsenic is As. So 4p3, if I was going to fill in my electrons correctly, would I go 1, 2, 3, like that? No, right? That's no good. I've got to go 1, 2, 3, right? See how now it makes a difference the order you fill them in? Because it would have put me on the wrong version of my orbital, everything, right? So the electron that I need to focus on is this one. All right, so as I go to write my quantum number, what's the first one going to be? 4. Okay, then I think about the shape, and I say S is 0, P, D, F. S, P, so it's going to be a 1. Then I'm looking at what version of the orbital am I at. So I'll label my orbitals 0, 1, negative 1. Okay, so this third part of my quantum number is going to be a 1, right? Because that's what version of the orbital it's on. And then the last part, is it going to be positive 1/2 or negative 1/2? That's it, right there. Easy, easy, right? Yes. You do. That's a good question. You can't just leave it if it's the positive version. You do have to put the plus. Yep. Yep. Have to have the plus. Okay, because if you don't put the plus, then I think you're just taking a guess. You know what I'm saying? And hoping that you got it right. Okay. Let's try another one. Find the quantum number for the last electron placed in carbon plus 2. Do you see a little wrinkle in things here? Carbon plus 2. Let's think about what has to change there. Okay. Does carbon have 2 extra electrons or 2 less electrons? 2 less. Good. So instead of carbon being 2p2, it's really going to look like 1s2. No, 2s2. Sorry. 2s2. Does that make sense? Instead of carbon being 2p2, it's really going to look like 2s2. So I'll go 2s.
Why is it 2s2?
Carbon usually would have 6 electrons, but since it's got a plus 2 charge, that means it's short 2 electrons. So we move back to only 4, and that's like beryllium, which is 2s2. Okay, so if I look at 2s2, I'm looking at this electron right here. Do we agree with that part? So let's look at our quantum number. My quantum number will start with a 2. What number is an s orbital? 0. Then what versions of that can we have?
0.
Yeah, there's only one version. And we said that the third one has to range from L to negative L. Or negative L to L. There's only 0. You can have negative 0. It's just 0. That's it. And like we said, if you start in the middle with labeling 0 and work your way out, that's really all you're going to have. So anytime it's an s orbital, there's going to be 2 zeros in a row. Okay? Anytime it's an s orbital, it's going to be 0, 0. Yeah?
Why is it an S?
Why is this one in an S? Because carbon has 2 less electrons than normal. And so it only has got 4 electrons instead of 6. So the first 2 electrons go in the 1s orbital, the next 2 electrons go in a 2s orbital. Okay?
So since it's 2s though, the s's, there's 2 of them, so
Right.
shouldn't there be like a second line?
We only are looking for the address of the very last electron. So the last electron that goes in, number 4, electron number 4, doesn't go into the 1s orbitals, it goes into the 2s orbitals.
So from how on the...
Yeah, if I was doing a full orbital notation, you're right. I would have 1s like that.
No, like on the 4p1, you still wrote out all 3 of them.
Right, because there's 3 versions of the p orbitals, but there's only 1 version of s orbitals, because each orbital can hold 2 electrons. There's only 1 version of s orbitals. Yes?
Wait, is there nothing that goes into the fourth one?
We just haven't got there yet. Is it going to be the positive or the negative?
Negative.
Negative 1/2, right? Because it's the one that's pointing downward. That's what we're looking at.
How do you know which one that is?
It's always the last electron. So we said find the quantum number for the last electron placed in C plus 2. So as we were filling out our orbital diagram, 2s, we went this one first, then that one second. So that's what we're looking at. Whatever goes in last.
Wait, how do you tell if it's positive or negative?
negative is pointing downward, positive is pointing upward. That's it. Okay? Try the last one here on your own, and then we're going to do a couple from the quantum number to find the element. Oh, never mind. I have this for you. Let me give you one more on your own. Give me the quantum number for the last electron in nickel. Give me the quantum number for the last electron in nickel. Uh-huh. Because nickel is in 3D.
Yeah, why is it?
Remember, the d orbitals are shifted 1, right? Even though it's in the 4th energy level, it's still considered 3D, not 4D.
Is the third one always going to be positive?
No. Because if we were looking at this electron right here, we would have said it was negative 2.
Oh, okay.
Right? It's just dependent on which electron orbital it's sitting on. This one happened to be sitting here.
Okay, thank
Okay? Yep.
Why is it a negative?
Why is it what?
Negative.
Because my electron I'm looking at is pointing downward. Right? It's the downward pointing one.
So, how do you...
What'd you say?
How do you know how many lines to make above it?
Right here?
Yeah.
Since this was a d orbital, there's 5 versions of the d orbital, right? Or think about the d block. The d orbitals can hold 10 total electrons. Each orbital can hold 2 electrons, so there's got to be 5 different orbitals there. Okay?
Oh, that's what I was saying earlier. But isn't there 2 versions of the S orbital?
No, just 1. Because s orbitals can hold 2 electrons, and so that's what the 2 of them.
So
Right? Over there, there's 6 in the p block. 6 divided by 2 electrons each is 3 versions. That's why we draw 3 lines for p.
Oh yeah, and then 2 can only fit in the 1.
Right.
And then the way you get 2 is that it was...
2, 0, 0, positive 1/2. So it's going to be beneficial for you to draw out that orbital and then figure out what electron configuration matches that, what element matches that. Okay, 2, 0 tells us it's what type of orbital?
Could you also,
2s.
do you have to draw it out?
No. No, you don't have to. It's a 2s orbital. This 0, there's only 1 version of it, so there's no need for us to really worry about that part. The positive 1/2 tells us, is it the first electron that went in or the second electron that went in? The first. So 2s1 tells me it is the element lithium. Okay, 2s1 tells me it's the element lithium. You want to try a couple more of those with finding the element?
Sure.
Okay, let's try. Okay, try that one. Okay, so this tells me, this -1 tells me it's going to be on this orbital right here. But is it going to be the first electron or the second electron? It's got to be the second. So can I fill in my electrons like this? No, you have to follow the rules for orbital notation. So 1, 2, 3, 4, 5, 6, 7. That's the electron I'm looking at right there. So 3d7 is cobalt, CO. How many of you had that? Good. How many of you I would just work too fast a little bit for you? Sorry. I know you're on your way there. Okay? The important part about drawing it from the from the quantum number to the element is that you've got to pay attention here and then fill it in the correct order. So negative 1/2 tells me I've got to fill in all 5 then until I get to that negative 1 orbital again. Okay?